To talk about marginal determinism as another property that allows suddenly things to become tractable.
Great, thank you, Guy, for the introduction. I'll be talking about marginal determinism in structured decomposable circuits. That's a lot of words, but it will hopefully become much clearer what this means in just a few minutes. Okay, so let's start by looking at probabilistic and logical queries. So there are a few particular types of queries which I want to focus on, which are relevant for this marginal determinism property. Now, the first one we've already seen a few times in the workshop this week. So this is marginal map. So the idea is that you have here a distribution over sets of variables Q and H, and then what you want to do is to maximize find the most likely instantiation of Q when you've marginalized out the other variables H. Another example which kind of fits into this the same sort of thing, which we've also seen, is trying to do some operations in factorized databases. So we saw a bit in Ahmed's talk that there are special conditions that you need in order to be able to do projection on factorized databases. And actually, it turns out that these two problems share a very close relationship. So here you have basically the join of some relations, and then you project onto this set of variables Q or set of attributes Q, and then you try to do a count essentially. And there are a number of other queries like marginal/conditional entropy for distributions, causal inference, which I will talk about more later in the talk, which also happen to require exactly this marginal determinism property. So yeah, hopefully at least one of these is of interest to you. So let's continue. So how have people looked at how to do this, right? How to actually be able to compute these queries. So I'm going to focus on exact computation. So I'm just going to look at cases where we can say, given a circuit or given some representation, we can find some way of computing this marginal map exactly in one go. Eugene presented a very nice algorithm for essentially sort of iteratively improving the estimate of the map until eventually it can converge exactly. But I'm just looking at essentially here circuits where you can just do this marginal map in one pass. So there are a few sort of formalisms which have been developed for saying when you can do this. One of these is so-called Q-valid pseudo-trees. So pseudo-trees we saw from Rena's talk when she was presenting and/or search graphs. And essentially what a Q-valid pseudo-tree is basically a pseudo-tree where the variables in Q appear at the top of the pseudo-tree. So here, for example, if Q was A, B, C, D, then this would be a Q-valid pseudo-tree. And this allows you to once you turn this into an and/or graph, it allows you to do a marginal map in a single pass. There are also these path-constrained F-trees in factorized databases. So this has a very similar principle. So essentially, if you want to project onto a set of variables, that means marginalize out the other variables, then you have exactly the same type of condition with these F-trees. Essentially, the variables which you keep, the Q variables have to sort of appear at the top of the tree. Let's look at another example. So we have elimination orders and so-called constrained elimination orders. So elimination orders are a way of doing inference in graphical models, essentially, or way of specifying how you do inference in graphical models. And so usually you would want to choose the elimination order, which gives you the sort of fastest inference, or equivalently the smallest circuit. But if you want to be able to compute marginal map with respect to Q, for example, then you need these Q-constrained elimination orderings. And what this means is basically the Q variables have to appear at the end of the ordering. And we also have these Q-constrained v-trees, which are a little bit different in that they sort of directly work on the v-trees that we have in sort of the general circuit representation. But you can still see that they have a very similar structure in terms of what makes this v-tree Q constrained. So the point here is that Q1, Q2, and Q3 are kind of before the other variable y in the v-tree in some sense. And so if you have a SDD, a sentential decision diagram, which or a probabilistic version of a sentential decision diagram which satisfies this Q-constrained v-tree, then again you can do marginal map or the sorts of things we discussed. So basically, we have a whole bunch of queries which we'll see are sort of closely related, and then we have a whole bunch of sort of formalisms for how to describe when or how you can do do these inferences. So what I'd like to do in this talk essentially is to try to come up with a circuit view of what it means to be able to do these, to be able to answer these queries tractably, because all of these and all search graphs, factorized databases, arithmetic circuits, SCDs, they're essentially circuits. So we want some sort of circuit property type framework where we can say, yes, this is the condition that we need specifically for tractability, rather than necessarily worrying too much about precisely where the circuit came from. Okay, so just an outline or sort of a summary of what I've been trying to motivate here. So we want sort of a unifying language for describing these kinds of circuits which can compute marginal map and the other queries tractably. And the reason that is then, of course, we can look at any domain where we have these sorts of problems and then just turn them into a circuit, and then we can just analyze the circuit using this sort of language, as always in knowledge compilation, right? Another advantage of doing this is that by sort of turning it into purely circuit language, then certain things become more obvious, or maybe not obvious is the right word, but easier to derive than if you looked at problem-specific frameworks. So we can maybe get some better understanding of what is really underlying all of these algorithms, which all essentially rely on circuits. And finally, I'm also going to talk a little bit about compositionality. So once we have this sort of language for circuits, then we can go ahead and not just look at marginal map or necessarily the queries I just showed you, but look at sort of what is, how far can we extend the range of queries which we can answer. Okay, so I'm now going to go into the sort of technical portion of the talk. Hopefully, we generally know what a probabilistic circle is now, but I'll still go over it just to be sure we're all on the same page. So a probabilistic circle is basically a rooted graph where each node represents a distribution over a set of variables which we call its scope and denote like so. And then essentially we have three types of nodes. We have leaf nodes, which usually correspond to simple base distributions, so maybe a univariate Gaussian or a discrete distribution. And then we have product nodes, which essentially make an independence assumption. So you have the product of the two distributions, and then we have these sum nodes, which are essentially mixtures of the components. Okay, and here's an example of a probabilistic circuit over 3 binary variables. So here are some of the key properties that we want. So decomposability says that the children of a product node have disjoint scopes. So it should be pretty easy to see here that this circuit is decomposable. If you look at any product node, then the set of variables which appear on one side are disjoint from the set of variables which appear on the other side. We also have smoothness, which is saying that the children of a sum node have the same scope. So again, you can look at the sum nodes and see that the children of the sum nodes mention the same set of variables. And finally, we have determinism, which is usually phrased as saying that the children of a sum node correspond to different values of the scope of the node. So essentially, if you look on the left-hand side of the root sum node, all of the x, y, z values which are possible on the left side are not possible on the right side, and vice versa. Another way of saying this is to say that essentially the support of the children are disjoint. And yeah, another way of saying it, if you want to look at it from a logical perspective, or if you're looking at a logic circuit, is convert this essentially into a logic circuit. Replace the sums with ors and products with ands, and remove the weights, and then you're basically saying that the conjunction of the two children formally is unsatisfiable. Okay, hopefully this is clear. So we've also seen structured decomposability. So structured decomposability is basically a stronger version of decomposability, which says that a circuit decomposes its scope in a particular way. So basically, we're going to say that a circuit structure is decomposable if it respects some v-tree. And what does it mean to respect some v-tree? Well, it means that the scope of the product nodes decompose according to the v-tree. So if we see, for example, the product node just below the root sum node, then you can see this decomposes the variables into x and z, and then y. And so this corresponds to node 1 in the v-tree. Yeah. And you can also see that the product nodes which split into x and z will correspond to node 2 in the v-tree. So it basically just means throughout the circuit, the decomposition of variables happens in the same way. So yeah, this circuit is structure decomposable, smooth, and deterministic, as I've explained. Okay. So now let's look at map inference before we look at marginal map. So map is basically this operation where you maximize the probability over all possible values of the variables. And okay, so how do we do that for this circuit? Well, we know that if the circuit is deterministic, then we can do this tractably in linear time. And how do we do this? Basically, you can just replace the leaf nodes with ones and replace the sums with maximizations, and then do a bottom-up computation here. So you can see here that we have the most likely state having 0.504 probability, and if you sort of follow the trace of what's going on here, you can also get the actual values of x, y, and z which achieve this. So basically, if we have determinism, we can do map inference. What about marginal map? So marginal map, the difference is that we're marginalizing out a set of variables, and then we're doing this maximization. So one sort of simple thing you can do is just write this literally as a composition of two operations, or a composition of two things that you're doing. So this marginalization is literally saying we take our circuit and we somehow discard the variables h, and then we go ahead and do this maximization, which we just showed how we can do. Now, what's the problem with this? Well, sometimes it works. So here I'm showing you if q is x and z and h is y, then yeah, all we've done is marginalized out y. We've gotten rid of that component. And now, if you look at this, this is still a deterministic circuit, deterministic and decomposable circuit. So, so actually, we're done here. We've basically said, okay, we can marginalize, and then we have a deterministic circuit, so we can compute the map, which means we can do the marginal map with respect to q. But this doesn't always work, right? So, if instead q was the set x and y, then this is what you would get from doing the marginalization. And what you see is that this is no longer deterministic. So if you look carefully, then for the root sum node, you see that both children of this root sum node can cover all values of x and y, right? And as soon as this happens, this means that we can no longer do map inference tractably. And so essentially we've run into a bit of a roadblock. Okay, so how do we sort of describe this condition, right? What is it about the circuit which makes it so that we can do marginal determinism, so we can do marginal map with respect to this q, but not that other q? So there's this nice definition by Yu-Jung, Antonio Yi, and others called marginal determinism. And so I'll sort of give you the formal definition, but don't worry too much about all the details. I'll give an example straight afterwards. So a sum node is q deterministic if where q is a set of variables. If this sub q for the children of that sum node are disjoint. What is this sub q? The sub q is basically the set of values of q for which that node has a positive value or positive probability. So another way you can see this is you can also just write this as a logical formula. You can also say, convert it into a logical circuit, look at the logical formulae, delta ni, delta nj, and then essentially do this existential quantification over the other variables. And then we say that a circuit is q deterministic if for every sum node, either this sum node doesn't mention the q variables at all, or it has to be q deterministic. So there's a lot here, but essentially this is precisely specifying what we need for this procedure that I just described to work. Okay. So here's an example. So this circuit is x, y, z deterministic. Why is that? Well, we sort of saw that it's deterministic, right? So for every value of x, y, and z, when you go to a sum node, then we have different values of this x, y, z tuple. And so this x, y, z determinism is exactly saying determinism, our normal determinism. We can also do this exercise for xz determinism. So basically, you check for all of the sum nodes that the children correspond to different values of x and z. And if you squint a little at the sum nodes, you'll see that this is true. And note the condition before where I said that either the scope doesn't overlap or it's q deterministic. So that's basically to cover the case where so you have these sum nodes which contain the variable y, and so we basically want to say we don't need this property for that sum node because we'll get rid of the y anyway. So this is just precisely saying the condition we need to do the procedure I described before. However, it's not XY deterministic. Why is it not XY deterministic? Well, this is because, as you can sort of see here, the children of the root sum node can have overlapping values of x and y, right? And this became very obvious when we marginalized out the z from the circuit. Okay, so basically, if a circuit is Q deterministic, then we can do marginal map for that Q. So in this case, we can do it for Q equals x, y, z. So that's just map because this is determinism. And we can also do it for Q equals x, z. Yes, Wolfgang.
Visible in the corresponding v-tree. So the template of this one. Do you have to go over the instance of the circuit?
So it's not visible or specified just in the v-tree. There are specific cases where you give additional semantics to the v-tree where it does show up, but no, generally no. Any other questions? If there's anything which is unclear, yeah.
Yeah. So what's the benefit of defining like this instead of just saying after you remove variable it remains deterministic?
Well, it's really the same thing. This is just a I guess sort of a precise definition. But if you look closely at what it's saying, it's exactly the same as saying you marginalize out the variable, because the marginalizing out the variable is saying that if the scope of the sum node doesn't overlap, then this basically means that we can just completely remove that node when we're marginalizing, right? Basically, if you marginalize them, what you're doing is essentially sort of moving to this support, and so this then because if you sort of marginalize all the other variables, or essentially existentially quantify the other variables, then you end up with this sub Q, and yeah, it's precisely the condition to say you marginalize out the other variables, and the circuit is then deterministic. Any other questions? Yeah.
Does marginalization preserve other properties like decomposability or smoothness?
Yes. Yeah. So yes, it will. Yeah, you can do it preserving decomposability and smoothness. Okay. Any other questions? Just so we're all on the same page. Okay, so now, sort of, I guess one thing to notice is that marginal determinism is not one property, right? It's not like determinism, in the sense that we can define marginal determinism for any subset Q of the variables. That's why we say Q determinism. So this is like a family of properties defined for each subset of variables Q. Okay, and so we would like some more systematic way of understanding what marginal determinisms are possible, or how these properties all interact, right? Because actually it turns out that there is no real simple relationship between different Q determinism properties. So for example, it's not the case that if Q is deterministic, then every superset of it, sorry, if a circuit is Q deterministic, then it's Q deterministic for a superset or a subset or anything like this. That doesn't necessarily hold. So for what Qs a circuit satisfies Q determinism, it's very unclear. so, for example, as I said, you might be interested in saying for a given circuit, what Q's is that circuit Q deterministic, and therefore can I use it to do inference and to do marginal map inference, for example, and also sort of how do I think about these Q deterministic circuits in terms of v-trees, for example. So what I'm going to introduce here is these md-vtrees, which are a template for marginal determinism in structured decomposable circuits. So you'll see what I mean by a template very shortly, but this is just the definition syntactically of what an md-vtree is. It's basically a v-tree where each node is annotated with this label psi of m. And this label is essentially either a subset of variables or it's equal to u, where u is the universal set. That means it's a superset of all other sets. So I'll sort of show you intuitively what this means. So the semantics are basically like this. So we're going to say that a circuit respects an md-vtree if it respects the v-tree, so essentially it's structured decomposable, and also that every sum node is psi m deterministic, where psi m is the corresponding v-tree node. So let's have a look at this example. So you've seen what I've added to these v-tree nodes is this set, right? Is a set for each node. And this is precisely the md-vtree label. Okay, and then what does it mean for a circuit to respect this md-vtree? Well, if we look at the top sum node, that's going to correspond to the top v-tree node, 1. And then what we're saying is that that node has to be xz deterministic, which means that the children correspond to different values of xz. And you can do this for the other sum nodes as well. For example, for the leftmost sum node, you can correspond that to the v-tree node 2. And then again, you're saying that this sum node has to be xz deterministic, which it is. Okay? So the way to think of this md-vtree is it's a template or a specification for a class of circuits or a set of circuits such that certain nice things are true about that class of circuits. And those certain nice things will be tractability, essentially. But yes, this is a template. Does this sort of make sense? Okay. So I'm not going to go into too much of the details in the interest of time, but I will touch on a few interesting facts about md-vtrees. And this is, I guess, my promise about there being some interesting things you might be able to see by working in this sort of like purely circuit-based framework, right? We're just talking in terms of v-trees and properties of nodes, which may not have been obvious in some of the previous, some of the other frameworks. So one interesting thing is that, okay, so firstly, the kind of point of defining this md-vtree is that it actually gives us a set of sets Q for which we can guarantee that the circuit is Q deterministic. So as in we can read this md-vtree, and that guarantees us that any circuit respecting this md-vtree would have certain Q determinisms. Okay, so that's what I mean by it's a template. And furthermore, what we can actually do is, it turns out you can enumerate this efficiently for md-vtrees. So here's the example. Basically, when we were going from the v-tree here, we go to here, where now what I'm showing is essentially a set of sets, yeah, a set of marginal determinisms. And at the top, we have essentially at the root we have these two sets of marginal determinisms. And this is precisely what we saw through our case analysis previously, where we saw that the circuit would be xz and x, z, y deterministic, but actually just through the md-v tree, we can efficiently, there's an efficient algorithm to essentially compute this. And this is this is great because basically we can just work on the level of the md-v tree when considering what tractability we have. Okay, so again, this is something which hopefully is not completely obvious. Let's move on to the second part. So now I've said that given an md-v tree, I can determine the set of marginal determinisms which it guarantees. Can we do something slightly different? So given a v tree, so this is just a variable decomposition and any set of marginal determinisms. So this is any subset of the power set of the set of variables. Okay. So S would be this xz and xzy set. It turns out there's a very simple algorithm for any v tree to be able to enforce this. And this is kind of surprising because a lot of the times especially with v trees in terms of how we think about this, we often assume that there has to be some sort of variable decomposition which then enables your marginal map. But it turns out that this is not the case. Really, the important thing is this sort of support decomposition, right? And this kind of gives you the sort of like direct sort of justification for that. So here, basically, we took our v tree and then we said, okay, we want this we want an md-v tree for this v tree, which is Q deterministic. And if you follow this algorithm, you essentially get this. And you can do this for any v tree, so any variable decomposition. So the kind of point here is that sort of scope and support decomposition are, in some sense at least, you can do them orthogonally. The catch is that this is not always a good idea because the expressivity of the circuit may depend on the interactions between the v tree and the marginal determinisms. But at least in principle, you can do it. This is one of the sort of things which is kind of, I guess, not so clear when you look at things like F trees and pseudo trees and so on, where the sort of support decomposition you do by conditioning on a variable is very much tied to the sort of to the scope decomposition as well in some sense. And okay, a third interesting fact is actually, there are loads of different md-v trees, right? Like we can label our md-v tree with whatever sets we want, but actually only a few of them make sense. Which of them make sense? Well, we're going to say which ones don't make sense. So an md-v tree is inadmissible if there exists another md-v tree which is at least as tractable with respect to marginal determinism. That means it implies all marginal determinisms which W implies. So yeah, intuitively, we have another md-v tree which is at least as tractable. But also, this new v tree is strictly more general, which means that there exists a circuit which is captured by this W prime, which is not captured by W. And also, of course, all circuits captured by W are captured by W prime. So this is basically saying, well, if we want sort of, intuitively, we want sort of the most general, the most general class of circuits where we have a certain tractability condition, then we can, then we don't want these inadmissible md-v trees. And one interesting thing we found is that essentially PSDDs, or more accurately, strong determinism, is actually not admissible. As in, you can do something better. Okay. So yeah, basically the summary of this is md-v trees are circuit templates. So they're designed in such a way that we're just interested in what sort of tractability guarantees we can get from this template. You can have your favorite method for generating circuits as an md-v tree, and then if we can sort of express this as an md-v tree, then we can do the things which I sort of described in the interesting facts. And another difference which might be a little bit instructive is that unlike some of these other trees, we don't really care about how the support is decomposed. We just care that it is decomposed in some way. So it doesn't. We don't have to sort of condition on all values of two variables. For example, we can do this split into two components, and it has no implication on tractability. Because I think I'm running out of time, I will sort of try to, or I guess probably roughly. I have no time left, right?
Spend a few minutes.
Okay, so I'm going to show the application of this to causal inference, which I promised at the start. So essentially in causal inference, or at least level 2 on the Perl hierarchy, you're interested in sort of quantities of this form P of y given do A. And this intuitively is the causal effect of A on y. In general, this is not equal to the conditional, and this is just saying correlation is not causation. And sort of what you can do is you can sort of specify some assumptions on your system in the form of a causal diagram. So these are two examples. And then given that causal diagram, you can actually write this P of y given do A as a purely probabilistic expression. Okay, but this expression will differ depending on the graph. So if we have the graph, then we have a purely probabilistic expression. So then we want to know when can we compute this probabilistic expression. And it turns out that this is essentially hard for structured decomposable, smooth, and deterministic circuits. So this is where marginal determinism comes in. But how do we sort of approach a problem like this, right? How do we approach a problem like this summation over products with conditionals? Well, one way of doing this, and this is a very nice paper which I recommend you all to read by Antonio Guy, Yu Zheng, and others, is to express this query as a composition of basic operations. So in this case, these basic operations are marginals, products, and conditionals. If you squint at this for a while, you can see that this is basically saying what's in the query above. And okay, so once you have this, essentially you want to analyze how each of these basic operations affects your md-vtree. And then by pushing this md-vtree forward through this composition, you can then check whether it satisfies the conditions you need for the query to be tractable. That's the sort of high-level overview. What do we mean by basic operations? Well, here's a bunch, and here's a bunch of sort of results on these basic operations. But suffice to say, for example, for database folks, marginalization is like projection, instantiation is like selection, I think, and then products are like joins. So these are just operations. And okay, so you can sort of use the md-vtrees and do a bit more work and combine it with this compositional inference framework, and you can figure out that actually, if you have a structure decomposable and a union Z deterministic circuit, then there is a quadratic algorithm for the causal effect. And of course, the formula differs for different graphs, but for these other graphs, we can also derive some polynomial time algorithms, which we didn't know how to do before. Okay, so that's for quickly some open questions. Do we have some good characterization of marginal determinism for non-structured circuits, or marginal map for non-structured circuits? This I don't really know. Any cases, I'd be very interested if anyone knows of any cases where marginal map is not, it is tractable through reasons other than sort of marginal determinism. So basically anything which wasn't what I described with the four the four trees. So when I described the difference between SDDs and these circuits and being tractable for the same thing, essentially, if we actually want a separation, we need to sort of show a separation between structured and deterministic circuits and structured and strongly deterministic circuits like SDDs. And as far as I know, there is no such result. So yeah, there's no question for anyone. So, yeah, okay, great. Thank you, and sorry for running over time.
Very nice. so we have time for one question, I guess. Well, the next speaker sits up. Do you want to ask it or not?
Comment a bit on this marginal determinism for non-structured circuits. Ideally, if you have a way to represent your hierarchical scope decomposition that's a region graph, when you can split every scope into multiple ways, different partitions, you can still annotate that. So, right?
Yes. Yeah.
So-
That's a good point. So if you have a sort of small number of components of structure decomposable.
No, I'm saying like the circuit is not structure decomposable, it's just decomposable, and you have the region graph, and you still annotate.
Right. Right. The union. Right. Yes. Yes. I think that's possible. Yeah. Yeah, that'd be quite interesting because we don't have to be tied to the V-tree.
Thank you for the nice talk. Maybe I missed it, but I was wondering if I give you two DNNFs that are structured along the same md-v tree, could you do the apply and still be structured along this md-v tree?
Yes, you can do apply operations even for just same V-tree, right?
Right. So then, and you keep this this determinism, right?
Yes. So actually, it turns out, and this is shown in the paper I referenced by Antonio and others, that actually, for sort of probabilistic circuits, you don't need determinism even. You just need structuredness to do products.
Yeah. But my point was, admit that you want to do marginalized MAP, and you know the variables you want to marginalize on, and you want to compile your problem into something that has this Q determinism.
Yes.
If you can do some bottom-up compilation where you ensure this Q determinism, then this is good, right? You can.
Yes.
So my question was, can you do that in a bottom-up manner?
In limited cases. So essentially, I think what you're saying is work backwards, right? You want some end product to be Q deterministic, for example, or deterministic, and you want to work backwards to figure out what you need symbolically in terms of the md-vtrees to get there. So in general, I think this will probably need some sort of computational effort to do. I have some sort of sufficient conditions which you can apply and see if they work, essentially. So working back and sort of figure out, if these conditions hold, then we can do this, but it's certainly not complete. Like there are, the actual analysis requires probably more case analysis.
I think the question is a little simpler in the sense that if I have two circuits that respect the same md-v-tree and I can join them or multiply them, will it respect the same md-v-tree again, or will you lose or add some marginal determinism?
Thanks, Sri.
Okay, thank you. So I think it will respect the same md-v-tree, but I have to.
That you could, and then you get automatically a compiler that can enforce some Q determinism. This is good.
I love that question.
Yes. Thank you.
Very good, thank you.
Good. I think we are definitely over time. So thanks, Benjie, again.
Thank you.